Welcome to Learning Machines seminars at RISE. Today it's my pleasure to introduce Andrew Jesson, who's a PhD candidate at the Applied and Theoretical Machine Learning group at Oxford University. He's under the supervision of Yarin Gal, and as many of you know, is the author of many groundbreaking results in Bayesian deep learning. Andrew has previously worked as a program manager and as a researcher at Imagia in Montreal. He has a master's in data science from McGill University. He's working on different aspects of uncertainty in personalized decision-making and in relation to causality. And among Andrew's publications, you can find topics such as nonlinear causal models for aerosol cloud interaction modeling and Bayesian active learning for treatment effects from observational data. The floor is yours, Andrew.
Well, thank you so much for having me, Olaf. So as Olaf has said, today I'm going to be presenting this work. This title that I've given it right now is Head in the Clouds, or Why Decision-Making is Hard. And so it's going to be sort of a two-part talk. One sort of focused on the focus of my thesis, which is sort of personalized decision-making and uncertainty in personalized decision-making, and then some applied work that we've started on, still very preliminary work, looking at the effects of aerosol cloud interactions. We're learning about aerosol cloud interactions from satellite data. I'm not sure I can see the chat. I'm totally okay if there are questions throughout the talk, if people would like to ask, but I just, in the setup I have right now, I can't see the chat. So if Olaf, you could let me know.
I will keep an eye on the chat and I'll forward questions to you.
Wonderful. So first off, just like to put a big thanks to my collaborators that I've worked on the projects that I will discuss today. So it's Peter Manshausen, Alison Douglas, well, especially sort of some joint first authors that I've worked with, Peter Manshausen and Alison Douglas on the aerosol cloud interaction work, Søren Mindermann, who worked very closely on sort of quantifying uncertainty for heterogeneous effects, and Panagiotis Tigis, who we did some recent active learning work for NeurIPS. So to start things off, just give a brief outline of the talk. And as I said, sort of the focus of my thesis is looking at uncertainty in personalized decision making. So starting off, the first section of the talk will be what is personalized decision making. Then I want to go into why should we be uncertain about the decisions we make for ourselves and others on behalf of others. How does uncertainty inform decision making? If you're forced to make a choice, how can you use that uncertainty to give the best choice, perhaps? How do we quantify our uncertainty about the effects of our decisions? Ultimately, how we can reduce that uncertainty rather than just making ignorant decisions. And then finally, we'll look into this applied problem where we're learning heterogeneous effects from large-scale observational data, this being satellite data and learning about aerosol cloud interactions. So that is the broad outline. What is personalized decision-making? Why should we be uncertain about decisions? How does uncertainty inform decision-making? How do we quantify it? How do we reduce it? And then looking at an application. So what is personalized decision-making? So personalized decision-making is concerned with these sorts of questions. Should I take an ibuprofen or hydrate to relieve my headache? Should I brake or turn to avoid an accident? Or should I study computer science or engineering to know about machine learning, or maybe stats or something like this? So while there may be population level trends to follow, rules of thumb to follow, maybe taking ibuprofen on the population level is better, maybe braking is better on a population level, or maybe study engineering is better on a population level, the best choice for you often can depend on you and your environment. If you were allergic to ibuprofen, for example, it would probably be better to hydrate or find an alternate treatment. So broadly, that's sort of the type of questions that we're looking at. And now let's get into why we should be uncertain about making those decisions, or what are the sources of uncertainty that would be present to make us uncertain about those things. So most of my work, although I started to look into some more experimental design things, has been focusing on learning about effects from observational data that already exists in the world, data where we don't have control over the treatment assignment mechanism. And treatment here we'll use quite broadly. It can basically be any intervention or choice that needs to be made. So observational data, typically we're dealing with some high dimensional covariates. For example, in the medical domain, that might be MRI imaging, electronic health records, genomics data, et cetera, et cetera, et cetera. For illustration, though, we'll just imagine these covariates. This picture of individuals is a one-dimensional covariate for illustrative purposes. And then in observational data, you have these populations, subgroups, one being a treated group, those that have received the treatment, and those that did not, or a control group. Then an outcome, for example, years survived after treatment, will be recorded sometime after the covariates have been measured and the treatment has been administered. So as I said, the essential difference, or one essential difference between observational data and experimental data, is that treatment assignment is typically not random for observational data, or we don't have access to the mechanism of how treatment was assigned to each unit in the population. And so there can be causal relationships between both the covariate values and the treatment assigned, as well as what we would expect is the causal relationship between the covariate value and the outcome. When there are these two such covariates that have this causal relationship between both the outcome and the treatment assignment, we call confounding variables. And if we want to know about how you will respond to a treatment, or how a treatment will affect your outcome, well, you need to be able to control for all confounders in order to know that. So when we're talking about making decisions for us, we need some sort of representation, some sort of picture of the potential confounding variables that would influence both treatment and our outcome. This representation needs to be sort of general enough that you can learn from a population of similar people, since for a given individual, you cannot see both the outcome under the observed treatment and the counterfactual outcome under an alternative treatment, but it also needs to be sort of specific enough that you can capture sort of this effect heterogeneity, the difference between how I would respond to the treatment and the difference between how you would respond to the treatment. So we kind of want to say, as this representation gets further away, so let's look at sort of how we would represent uncertainty, perhaps, in decision-making based on heterogeneous effects. As your representation sort of gets further away from the data manifold that we're learning from, we would expect our certainty about the response to become greater as we move away. Furthermore, if you were only given one choice, if you were, for example, excluded from treatment or always given treatment, well, we should also be uncertain about your response because we don't have a population for the counterfactual or for the opposing treatment. And then also, if we're not including that full picture, if we're not including all confounding variables, those associated with the treatment, your treatment assignment and your treatment outcome, well, then we should also be uncertain about the treatment effect. There are many, many more reasons, actually, why we should be uncertain. We focus mainly on these. One that I want to point out quickly, which is sort of pertinent to the application that we'll go through last, is in real world data. Well, we're kind of confronted with this. We have proxies for everything. So we have proxies for the confounding variables. We don't actually get to see the true confounding confounding variable. We see some measurement of it, and that measurement can have noise in it. We see proxies for the treatment sometimes itself, a noisy version of the treatment assignment, and we see proxies for the outcome as well that we might be interested in, when the true world that we might be interested looks something more like this, where we have sort of the true physical causal mechanisms obscured by these proxy variables. And so this can be another source of uncertainty. We won't go too deep into that today, but a nice example of this is sort of a typical example of this classical example is measurement bias, where if in your input space, let's say in the covariates, you're observing, let's just say here we have this example where we have X on our X-axis, and we have Y, our outcome, which is being some sine function of X plus some noise on the Y-axis. This being sort of the relationship that we want to know, let's say what's going on in the lighter shaded variables or graph. But what we actually observe is some noisy version of that X. Here we have just W equals X plus noise, classical attenuation bias results here. And the function that we will end up learning is actually a biased function of the true underlying data, underlying mechanism that we're interested in. So to recap, those sources of uncertainty, why we should be uncertain? I or you or I may not be represented in the data. You or I may have been excluded from receiving the treatment or always receive the treatment, perhaps because it would be unethical not to prescribe the treatment. We may not be modeling all the variables to get that complete picture of you to learn the true treatment effect. And finally, we may be seeing noisy versions of the data. We may not have access to those true causal mechanisms directly. And all of these ways are reasons why we should have some uncertainty when we are sort of learning about the treatment effect, that sort of basis for a decision. I make a decision assuming that I know how perhaps I would respond or what my outcome would be under that decision. And these are the reasons why we would be uncertain about those. So let's make the link now a little bit more concrete between treatment effects, how I respond to a treatment, and decision-making. So we'll go a little bit one level lower and start looking at some math. And in the literature, we have to learn about sort of these personalized effects or heterogeneous effects. Typical measurement is the conditional average treatment effect. So the CATE is expressed as the expected difference in potential outcomes at a measured covariate value. So let's go back to our simple observational data set. We have the covariate value on the x-axis, and we have our observed data in the top pane, our outcome on the y-axis, and our two populations, the treated in purple X's and the control in blue circles. So the CATE function is sort of trying to measure in the second pane the difference between these expected outcomes. In blue, we have our expected outcome for the control, and purple, our expected outcome for the treated. The difference in these two expected outcomes is then our treatment effect. Now the CATE is expressed in terms of these causal quantities. These causal quantities that we cannot really know from observational data, this expectation between the difference of potential outcomes. So let's break this down and sort of try to understand what's going on here. So conditional average treatment effect, everything we need to know is in the name. So conditional, it's conditioned on the measured covariates. Average, it's an expectation over the treatment effect, the difference in potential outcomes. What would have happened had you been treated versus what would have happened had you not been treated. So if we want to then make decisions based on the CATE, a simple treatment policy could just be treat if the CATE is positive and don't treat if the CATE is negative. Same thing essentially. But what happens when we can't identify the CATE? And there are many reasons. why we cannot identify the CATE. And now we'll go through those reasons and sort of link them to those sources of uncertainty before. For example, in this range, well, I don't really know what the expected outcome for treated is on the left-hand side, or I don't really know what the expected outcome for control is on the right-hand side. So what do we do in that case? In order to sort of express this as statistical quantities, we have to go from this difference in potential outcomes into some statistical estimator here. So our statistical estimator here for the CATE is then this expectation of the observed treatments minus the expectation of y over the covariate values under treated, observed treated, and expectation of y under covariate values x under observed control. And the CATE estimator, statistical estimator, is going to be this difference between the two in the purple on the bottom. So in order for this statistical quantity to be identifiable or to be equivalent to the causal quantity, we have to make some further assumptions. The first assumption being consistency and non-interference. So the outcome that we observe, the y that we can observe in the world, must be sort of the potential outcome under the assigned treatment. Unconfoundedness. So conditioned on our covariates, the potential outcomes, the set of potential outcomes should be independent of the treatment assigned. This is a little bit of a weird one in terms of how it's written, but it's almost like saying, well, the potential outcome is kind of predetermined regardless of whether or not of the actual treatment assignment. You would, like, the treatment assignment is not going to change the value of y1 itself. Or treatment as t equals 1 is not going to change the value of y1 itself. And then finally, overlap. So for a given value x, our propensity for treatment, the probability that we would observe a treated or a non-treated value is going to be 0 for each of t equals 1 or 0. So if any of these assumptions are violated, we should be uncertain about the CATE. So in the last section, we look at why should we be uncertain about personalized decision-making, and now we sort of link that with why we should be uncertain about not satisfying these assumptions that allow us to go from causal quantities to statistical quantities. So now that we can sort of express this, maybe we don't want to just say, treat when CATE is greater than 0, don't treat when CATE is less than 0, and we say, well, we should treat when we're certain that the CATE is greater than 0. So when given our uncertainty due to lack of overlap, our uncertainty because we're not represented in the data, our uncertainty because perhaps we believe that there could be a hidden confounder that we're not modeling, when all of those things are taken into account and our CATE is positive, then maybe that's we should treat. Likewise, don't treat, don't recommend, don't make the decision, or don't decide on this particular choice if the value of the CATE for that choice is less than 0. And we defer recommendation perhaps when we're uncertain about the sign of that CATE. Now the issue there is no decision is unfortunately still a decision. So what does deferral mean? Well, maybe in time-sensitive cases, we would want to defer to a safe policy or a domain expert. Otherwise, perhaps we would be interested in trying to reduce that uncertainty. And I think that's ultimately what we would be interested in. If I don't know how you are going to respond to a treatment, in time-sensitive case, we may still have to come up with a decision, but ultimately we would want to go out, learn more about you, and become more certain about how you are going to respond to that treatment. I'm not sure if there are any questions yet, but if there are not, we can sort of look into how can we get these ranges. So how can we quantify these effects?
I have a question, if that's okay.
Yes, of course.
Typically in these in this setting, do you know if people use different CATE estimators as they've been learned from, let's say, different studies, but that observes the same thing? So differences in CATE, do you know if that's actually used to identify confounding variables or not? Because I guess the difference could indicate a confounding one.
So do you mean like you would have one estimator trained on one data set that included these variables, and another estimator that's trained on a separate data set that included a different set of variables, and looking at the difference between those two estimates as an indication of whether or not there's hidden confounding?
I would say it would be the same variables, but different studies.
The same variables, but different studies. So I'm not sure if that would be an indicator of confounding.
Mm-hmm.
If it was the same variables on different studies, I suppose that's an interesting question. So there is, I don't want to say no right out, because you would say there is going to be some unexplained variance in both cases. But as both data sets, if they're the same variables, as both data sets tended in size to infinity, then the estimator from each would converge to the same value.
Yeah. So, I mean, the reason why I'm asking is that, let's see how I should put it, but I mean, we can probably pretty safely assume that, just like you said, each individual data set will have a number of different confounding variables, right? And it could be that there are actually different confounding variables between the two studies or the two data sets. So kind of what I'm fishing for here is, I mean, usually you have these spurious correlations between two different data sets. So essentially what I'm asking for is if the CATE value could be used as a way to identify some spurious correlation. I mean, kind of in the downstream task. So if you could feed the CATE information back into some model somehow, could you kind of force the model to kind of avoid that spurious correlation and not just do random sampling over both data sets?
It's very interesting. That's very interesting. I'm not 100% sure. It reminds me of recent work from one of my collaborators, Uri, that was looking at sort of invariant prediction across different domains.
Yeah,
exactly. And there's other work sort of going on in that, sort of the invariant risk minimization and descendants of that work.
Exactly. So that's kind of where I was coming from as well. So specifically, if you knew if CATE had been used in that setting or not. But
so I'm not 100% sure of CATE itself being used in that. I do know that there was recent work from a collaborator that was looking at invariant prediction across different domains. So I think that might be an interesting place to start looking. Okay. And I know that he's done work on heterogeneous effects as well, but I don't know if that paper is precisely about invariant estimation of heterogeneous effects.
Yeah. All right. Okay. Thanks.
Wonderful. If there are no further questions, I guess we can go to the next set. So let's look at, so this is now we're going to look at some work that I've done with others over the past 2 years that looks into how we can sort of quantify our uncertainty about the effects of decisions. So first, we're going to look at work from NeurIPS 2020 with co-first author Zoran called Identifying Causal Effect Inference Failure with Uncertainty-Aware Models, and follow up to that, which with the same group of collaborators, quantifying ignorance and individual level treatment effect estimates under hidden confounding. So in the first case, we're just looking at violations of the overlap assumption, and now we're sort of, and then in the second case, we're looking at doing a causal sensitivity analysis to account for violations in ignorability or the unconfoundedness assumption. So let's start with the first bracket there of uncertainty, which is quantifying uncertainty due to insufficient similarity and overlap. So if I'm not represented in the data, or if I've been excluded from treatment. In our specific approach, remember, we're going from this causal quantity, the CATE, into a statistical estimate of that causal quantity. So to model those statistical estimates, we look at taking a parametric approach. And specifically, we want something that is going to be able to scale to very high dimensional heterogeneous data. So we use neural networks in that case, Bayesian neural networks in that paper itself. So a neural network has a set of parameters, the weights, and those weights are going to induce a function that we can use to estimate the expected conditional outcome. In this case, we're looking at the treated group from the simple example before. So on the training data, it's quite clear what that function should look like and can estimate sort of our observed expected value quite well, or our non-parametric expected value quite well. But what should this function look like as we move further away from the data? The nice thing about taking a Bayesian approach here is that instead of just learning that one set of weights, that maximum likelihood set of weights that explains the data, we instead want to learn a posterior over those weights, such that we can sample from that posterior and get different explanations of the data different functions that equally explain the data. Or equally well explain the data. So if everything's working correctly, those functions should agree on the support of our training data, and they should disagree outside of that support, where it should, in a Bayesian setting, revert to the prior outside of the support of the data. A prior over functions, a prior distribution over the weights, which induces a prior distribution over functions. So what has been called in the literature epistemic uncertainty is a measurement of how much these functions disagree with one another. So this is in the continuous case. We can go quickly through a case where we have a discrete outcome. We have some observed data. We want to learn a function to predict y for some measurement x. Bayesian models learn a distribution over those functions. On the observed data manifold, the functions agree. Off the observed data manifold, they should not. And epistemic uncertainty is sort of a measure of this functional disagreement. So it's going to be low on the training data and far away, or on the data manifold, observed data manifold, and far away from it. So it can tell us when, in that way, a measurement lies outside of the domain that we have knowledge about. So now we can sort of frame non-overlap or exclusion from treatment, or always inclusion in treatment, as a covariate shift problem. So we start with this data set, and if we sort of have this example here where we can look at a data set that has this region of no overlap. So we have our response for the untreated in the top pane and our response for the treated in the bottom pane, and we do not have data for the treated in the bottom pane. So we can fit sort of Bayesian functions to these data, and in regions that are out of distribution for both the treated and control groups, we get high epistemic uncertainty, high disagreement between functional values. But moreover, in those non-overlapping regions, which is just out of distribution for one of the two data sets, we also get higher epistemic uncertainty. So in that way, epistemic uncertainty can be used to sort of define policies to defer a decision when there's insufficient knowledge about the individual. In that paper, we show how using the law of total covariance, or sorry, law of total variance, we can break down this variance over unidentifiable difference between potential outcomes as the variance over the expected values or the variance over the statistical CATE estimator. So we start from a variance and uncertainty and expected potential outcomes. We can decompose into these two terms, and our uncertainty in the CATE comes out naturally from that. We can also take an information theoretic approach to this and show that the mutual information in the difference but in unobservable potential outcomes can be estimated by this variance, or actually 1/2 log variance of this same difference. So that sums up this part. Other uncertainty-aware heterogeneous effect estimation, we can give shout outs to a recent work looking at addressing positivity violations in causal effect estimation using GP priors, work from Ahmed Allah and Michaela van der Schaar looking at Bayesian nonparametrics for causal inference, Athley and Wagner looking at causal forests, Jennifer Hill, BART, classic one, and recent work from our group, led by Just van Amersfoort, who looked at using deep Gaussian processes for this problem. Or actually, we just applied that method to this problem, which worked quite well. So now we can sort of look at the second problem. So that's looking at how can we sort of quantify uncertainty if one is not included in the data. But now, what do we do about uncertainty due to insufficient context when the hidden confounded, when the ignorability or unconfoundedness assumption is violated? The tricky issue with this assumption is that it's not testable given the data alone. So we have to bring in some prior knowledge. Another problem here is that a Bayesian approach is just not enough because of the untested. Because this is not a testable function given observed data. It's simply not a Bayesian approach. Is just simply not enough. Like we can. When we have hidden confoundedness, when we have hidden confounding, the result is that this can bias our CATE function. It can arbitrarily bias our CATE function in either direction. We can get a biased high estimate, we can get a biased low estimate. Just using model uncertainty is not going to tell us about the bias, this delta in between the true CATE, which we have in the dashed line, and our distribution over CATE functions, which we have in the purple lines here. That epistemic uncertainty, this disagreement is going to be high when there's no overlap and outside of the data distribution, but on the training data, it's going to be quite low, regardless of this actual bias that exists in our estimate. So we need something more. So we look in our work at doing a causal sensitivity analysis derived from the work of Callis, Zhou, and Mao in 2019, who used this marginal sensitivity model and a non-parametric approach to solve this problem. So our framework, instead of sort of taking this non-parametric approach, we take a density-based approach, and in order to sort of be able to scale this up. It's a nice framework. It doesn't require a specific learning model. All we need is basically just a density estimator for the outcome conditioned on the inputs and the treatment. It doesn't make assumptions about the hidden confounder, and it scales to large high-dimensional data. So as we said, since violations of ignorability are untestable from data, the practitioner is able to incorporate prior knowledge about how the hidden variable affects the propensity for treatment by specifying this parameter gamma, and the ignorance region grows with increasing gamma for a given measurement x. And using the results in KMZ 2019, we show that this for CATE estimates, this results in tight bounds, and we show that those are sharp bounds, and we show in our paper that those bounds are also sharp for the CATE itself. I don't know if we'll go too much into details on this, but in the end, so the other thing that we include there is to unify that uncertainty measure. So taking the work from NeurIPS 2020 and apply and incorporating into this sensitivity analysis that we extend from KMZ 19, we also include these bounds or confidence interval due to uncertainty about our CATE estimates, so uncertainty due to violations of overlap, or if you're not represented in the data, to get this ignorance measure of the treatment effect that includes both of these factors. So that was the contribution there, and that's there is some work also in that. I can give a shout out to work. So there's quite a bit of work now on conformal analysis that is sort of combining a sensitivity analysis based on conformal analysis, and then frequentist approaches to taking these confidence intervals. I think this recent work from David Bly's group. I meant to write all this down. Also work from Chernozhukov and others. And well, there's quite a bit of work going on right now. Guo and Dorn that also have these sort of unified measures of ignorance for treatment effects. So as we said before, there's still other sources of uncertainty. This is still a very big problem. So what happens, what uncertainties do noisy proxies for confounding variables induce? What intervals does measurement error produce? So there's still quite some work to be done along these lines. Finally, on the third trajectory, so how do we make decisions given uncertainty? How do we quantify uncertainty? And then finally, if we have the chance, let's go out and try to reduce our uncertainty about the effects of decisions. So briefly here, I'll just go over that quite briefly before going into the applied work. One thing that we looked at so far was sort of trying to do active learning when acquiring an outcome is costly. So this work is called Causal, Deep Bayesian Active Learning of Outcomes to Infer Treatment Effects from Observational Data. I was co-joint author with Panagiotis Tigas, along with Jos van Amersfoort, Andreas Kirsch, Uri Shalit, and Aaron Gall. So we're looking for this sample efficient strategy to acquire outcomes for observational data. Something I really like about this, just looking at a random acquisition. So let's say we have a data set, we have a pool data set consisting of observed treatments and covariates, or treatment assigned and covariates. And we want to acquire data to label because labels might be expensive. For example, if the label is a biopsy to get ground truth on a cancer status. What I found, like, I don't know, I like sharing this experiment because I think it's kind of interesting. So random acquisition has this very clear failure mode where it will oversample from the mean. Oh, it's not going to oversample from the mean. It's going to put most of our resources on samples from the mean, just by virtue of uniformly sampling over your data set. Sorry, the modes of the data set are going to be quite frequently, or more frequently sampled from than other parts of the support of the data. So what does that do in the end? Well, it sort of biases our acquisition of the mode, and it also biases what we learn about the function. So we kind of trade off accuracy in low frequency data for sort of certainty in the mode. So oversampling from that mode, such that when we go further away from the modes of the data, we don't really have an accurate example or estimate of what's going on with respect to the treatment effect. I should have set up this example a little bit more, but effectively we have our same example from before. We have regions where there are no overlap. Ultimately, our methodology wants to focus on regions where we do have overlap. We want to be uncertain when there's not overlap, but we want to be able to, sometimes when there's weak overlap, and Alex Dalmore has done quite a lot of nice work about weak overlap in these regions of weak overlap. Well, where we can learn about treatment effects, well, we should be sampling from there. And when we do random sampling, it's less and less likely that we would actually sample from those regions. So we may be able to learn something there, but we don't, because we don't sample enough from there. And we come up with a solution using an information theoretic approach that sort of balances that sampling across the domain of the data for which there is overlap. And we have some nice results. So now perhaps we can go into the application, and I realize that it's probably a bit of a sharp turn to go from decision making to learning about aerosol cloud interactions, but it's quite a nice applied project to sort of try to learn about treatment effects or heterogeneous effects from very large scale data. So this is work, this is preliminary work. We submitted it to a workshop at NeurIPS this year. We're currently doing quite a bit of follow-up on it. Joint co-authors, Peter Manshausen and Alison Douglas, and with Duncan Watson-Paris, Yaron Gal, and Philip Steyer. So this is work between the Oatmeal group, which Yaron leads, and I'm a part of, and the AOPP group, Aerosol and Oceanic Particle Physics group at Oxford. So aerosol cloud interactions. So the problem here, or the interesting thing about this is, as aerosol is emitted into the atmosphere and enters a cloud, it interacts as a cloud condensation nuclei. So that's something that water vapor, I believe, again, I'm going to make a lot of borderline statements here because this is not quite my area of expertise, but I think I have an okay understanding of all of this. So aerosols interact with water vapor in the cloud, and that acts as a cloud condensation nuclei. I also want to thank very much Alison Douglas for these slides that she made for our presentation at NeurIPS, at the workshop. So increasing the number of cloud droplets, so that aerosols act as a CCN, it creates new cloud droplets. And as the number of droplets increase, the mean droplet radius decreases. So aerosols go in, we get more droplets, smaller droplets. This higher number of smaller droplets creates a more reflective cloud. It creates a brighter, so it's a brighter cloud. It lasts longer because rain, precipitation, it happens as the droplet size gets bigger. So we have these small droplets. It causes a longer lasting cloud. It causes a brighter cloud. That brighter cloud is reflecting sun away from the Earth, and it has this net cooling effect. But But these effects, these aerosol cloud interactions, this cooling, this reflectivity, depends on many different environmental conditions. So that's where the heterogeneity comes in. So the magnitude and sign are heavily dependent upon local environment surrounding the cloud, and the aerosol can decrease. Yeah, so all of these increases, decreases depend on sort of these environmental interactions. So we use sort of large scale satellite data to learn about these interactions. So this is data collected, I believe, from 2003 to 2020. It covers the whole Earth, but we focus on a region in the South Pacific, and we get the data we use is taken as daily means. So it's once per day, and you have a 1 degree resolution of the Earth. So we have millions and millions and millions of data points over 20 years of roughly 2003 to 2020, 17 years. So there are a lot of issues here. So first of all, as we said before, our measurements are sort of proxies for these underlying physical mechanisms that are happening. So we have to sort of think about confounding due to that. You can only observe our treatment thing, which is the aerosol optical depth. How much aerosols are we putting into the cloud that affects sort of how bright the cloud is. This can only be observed in cloud-free scenes. So you have to sort of have some infilling there by a physical model called reanalysis. AOD itself is a proxy for the aerosol concentration, and AOD is also affected by nearby clouds in the local environment. So from a causal point of view, again, so we have our proxies for the environment, we have our proxies for the ARD, and we have our proxies for cloud properties, and that's reflecting this underlying causal structure where temperature and pressure affects supersaturation, which is going to affect our aerosols, which is going to affect the cloud droplet number, which affects the brightness, and so on and so forth of the cloud. So again, we kind of like went over our methods. We also look at using causal forest to understand what this treatment effect is. We look at different features from the environment, relative humidity, estimated inversion strength, sea surface temperature, vertical winds, our treatment thing. In this case, we looked at just treating the AOD as a binary variable. We're currently doing follow-up work to sort of look at something a little bit more complex. So if AOD is greater than, I think it was 0.12, we would treat it as a polluted environment. And if it was less than that, we would treat it as a pristine environment and just look at the difference in effect on our mean droplet radius, which is really our primary focus there, given quote unquote pristine versus polluted, but really just high AOD versus low AOD. So there's not really a ground truth in this. So we really wanted to look at two different models. The model that I described in the second section here with causal forests, which is another method. And while the numbers were slightly different, we saw the same sort of general trends as we looked at how the effect size changed as the CATE and the effective radius changed as we varied the individual covariates on their own. And we saw similar patterns looking at sort of pairwise comparisons between the covariates and the outcome as the effect of AOD, so the CATE again, and we saw a similar pattern between using Quince and causal forest as sort of a sanity check there. And these methods allow sort of as climate scientists to maybe look and evaluate these models for their own thing. So we also looked at sort of the average treatment effect. Given this setup, similar magnitude and the same sign for the average treatment effect between Quince and causal forest. It was a slightly higher magnitude than we did for linear models. But again, this is all very preliminary work. and we're not making any strong scientific conclusions yet. This is sort of exploratory into how we can use these nonlinear causal models to sort of estimate effect heterogeneity for this problem of aerosol cloud interactions, which there's still quite a lot of uncertainty about just what the effects of aerosols are on these cloud properties. So I think that's all for now. I just want to say thank you very much, and open up the floor for any questions that people might have.
Thank you, Andrew. Do we have some questions for Andrew?
Possibly, I may have a question. Anders Holst here. This gamma in your, was it the second part of your talk, that is for the confounders? When you didn't, you made a Bayesian guess of the effect of the confounders, because otherwise you couldn't say anything. But the whole point of unknown confounders is that you don't know that you have them. So how can you even guess how big the effect will be? As we know from the Simpson's paradox, a confounder can completely turn around the direction of the correlation or the size. So we don't know. So how can we produce a Bayesian prior for it?
You're absolutely right. And actually, our method does not do a Bayesian prior on it right now. It uses sort of the marginal sensitivity model, which proposes a relationship between the nominal propensity and the odds ratio of the nominal propensity, the propensity that we can identify from data, and the complete propensity for treatment, which we cannot identify from data. And you're absolutely right. We cannot know the magnitude of gamma here. That's absolutely, I'm definitely not making that claim. But what we can do, as with sensitivity analysis in general, is that given an assumption on that magnitude of gamma, given that our true propensity for treatment differs from, or the odds of our true propensity for treatment differs from the observed odds of treatment by so much, we can produce a bound on that treatment effect. So that can be used in two different ways. One, you can go to the expert and say, what is that bound? What is that bound on the odds ratio? Or what is that level what is that ratio that you would expect for this thing, and then get that for this problem, and then get that bound? Or, so Tan also proposes another approach where you can grow the region until that crosses the zero boundary and report that gamma value, that ratio between odds ratios, and make judgments on whether or not that's a sensible assumption. But you're absolutely right. I mean, it's fundamentally limited in that way. That's as strong as we can sort of get. We can't know the gamma from the data itself.
Okay, I see.
Do we have some more questions? So I'll have a question. So for this, the cloud interaction work, sort of how was this received by the climate researchers?
So it's interesting work, but I think the biggest criticism is, why are you treating AOD as a binary variable? So we should be looking at that as a continuous variable. Yeah, so it's interesting work. I think that going deeper into the causal structure, I think it was appreciated that we teased out this causal diagram, and we can start looking at at sort of the assumptions that we're making when we're reporting this number, this treatment effect. And I think it was received quite well. I think it's definitely something that needs to have more work, more attention on, to sort of get to hopefully a scientific contribution along those lines. But I think the first direction is, let's move from binary high-low and let's look at sort of the continuous effect, or the effects of continuous AOD.
So is that something you're planning on doing?
Yeah, something that we're currently working on.
Hmm. Cool. Do we have some last questions? Otherwise, we'll thank the speaker. Thank you, Andrew, for coming here and for this nice talk. Next week, we have a visitor from Norway, Jon Nordby. We'll be talking about audio analysis using machine learning. So thank you. See you next week.
Thank you so much.